VxWorks.
Great. Thank you for the introduction, Steve. So as he said, I'm Artem, and that's Peter. We're coming to you from Trail of Bits. Trail of Bits, for those who don't know, is a small New York-based security company. Neither of us is from New York, though. We both are remote employees. I'm actually local here to San Diego, and Peter's coming to us all the way from Ontario, Canada. And there we go. So there's a third person mentioned on this slide. Trent couldn't make it today, so there's just the two of us. And today we're going to be talking to you about PowerFL, which is a bug finding capability for VxWorks targets running on PowerPC and the Intel x86 platform. The approach we take in PowerFL is operating system agnostic and generalizes to other embedded platforms, such as automotive and SCADA systems. And we're not just going to describe how PowerFL works, but we're going to discuss the reasoning behind our design decisions and how embedded fuzzing differs from fuzzing more traditional PC-based targets. So first, we wanted to properly set some expectations and clearly state what we accomplished and what we have not accomplished. So we have a prototype that successfully uses AFL and QEMU to find bugs in VxWorks targets for both x86 and PowerPC. This does not mean that you can point it at an arbitrary firmware image and that bugs will fall out, contrary to some people's expectations. Also, most targets are not going to work out of the box. Bringing up a new target that you're going after with this still takes considerable manual effort. It really helps if you have documentation. It helps even more if you have source code. But you can still do it without any of those things like we had to. And we're going to talk about some tools and techniques that make this process easier. But bringing up a whole new target in the fuzzing platform is probably going to involve a fair bit of reverse engineering. So how did we end up doing this and how did we get here? So first we have to rewind back a few years to the DARPA Cyber Grand Challenge. We showed that machines could find, exploit, and fix bugs in arbitrary programs without human intervention. We were one of the competitors, and it led us to develop a pretty good automated bug finding capability. And when people hear about this, they get really excited and they think that this is immediately going to solve all of their security problems. And so we had a very serious customer come up to us and ask something. I'm going to paraphrase a lot here along the following. And they're like, hey, we want to deploy your capability on some custom software that we have. And we're like, oh yeah, we can totally do this. We've ported several open source applications to this, like libOTR and a few other things to help find bugs in it. And they're like, yeah, we can do this. It might be a few challenges. And they're like, great. Our target is VxWorks on PowerPC. When can you start? And we were like, whoa. Like, we have to explain a few things to you guys. So first, the Cyber Grand Challenge was like a big sandbox for toy programs. And the programs that the CGC machines exploited were very well defined in terms of what they could do and what their interfaces were. And we don't want to trivialize the Cyber Grand Challenge here. We know that the challenges were real programs that they did complex tasks. The vulnerabilities they had were very realistic, and some of them were extremely hard to identify and trigger. The challenges are very, very well done. We don't want to take that away from them. But the Cyber Grand Challenge really ignores a key part of trying to get a target up and running, which is if you get an unknown program, you don't actually know how to talk to it. And real software has a fairly unbounded way, not unbounded, but a fairly diverse way in which you can get input. And if you get a truly unknown program like you would in the embedded world, you may not even be able to run it. And so you may find that trying to get something to run actually takes more time than finding bugs in it. As an example, if you have an embedded program that reads some kind of firmware data from ROM and you only have the program and not the ROM data, you're going to have a hard time figuring out where that ROM should be located or what kind of data you're even going to be reading. I guess it's a long way of saying that in the real world, programs are not as cut and dry as in the automated world of the Cyber Grand Challenge. However, this project seemed extremely interesting to us for a few reasons. And the customer really wanted to have some kind of capability because currently they had nothing. So anything they could deploy in an automated fashion to their software would be better than what they currently had. And after some negotiation, we agreed to do it. And we were promised that we would get detailed documentation and expert support on the systems that we would be looking at. And after we agreed to take it on, we realized that the support and documentation were not going to materialize. This is not the customer's fault. They ran into some serious bureaucratic challenges on their end getting it to us. So they did promise it in good faith. But at the end, we had 2 firmware blobs. We were able to identify that one was for x86 and one was for PowerPC. And we had a very short time tasks to go and develop a system that will automatically find bugs in them. And so this talk is about how we would bring up a semi-automated bug finding platform for a relatively unknown embedded system. Well, we did know one thing. We knew that we'd be dealing with VxWorks. And we wanted to talk a little bit about what VxWorks is, for those of you who are unaware, and why it's important. So our system of choice was VxWorks, and the reason for it is that VxWorks runs on a very large variety of big physical systems, like cars, trains, SCADA systems, and other large things that drive, possibly drive on Mars. Mars rover runs VxWorks, fly and orbit and do all kinds of cool stuff. We can't really use traditional bug finding tools here because number one, they don't really necessarily work for VxWorks, especially for older versions. And also, you run into the problems that it's oftentimes possible that there may be just one of these systems, or that it's deployed doing something mission critical, or that you're really worried about giving it the wrong inputs because it very well may explode. And also, you're probably not going to get source code. You may get documentation. A lot of these things are either really old or something happens where for bureaucratic or other reasons you are simply not permitted to see it. A little bit more about VxWorks in a technical sense. And I'm going to apologize to the actual embedded developers here. I'm probably going to butcher a few things, but I think it's important to give this overview for people who are used to traditional operating system development like we were and aren't really familiar with embedded real-time operating systems. So VxWorks, as I said, is a real-time embedded operating system that acts effectively like a library that your program depends upon. It's extremely modular so that no 2 installations may be alike. And while it has all the bells and whistles you would expect from a traditional operating system, it's highly configured. So like you can select, for instance, not to have a serial port. You can select not to have a display driver. You can configure it to only work on a specific processor with a fixed amount of memory, which is all configurations that we ended up looking at. And there's usually 2 different ways to use it. There is the thing where you kind of compile your program in VxWorks. And so you set up your configuration, you write your actual program, and what you end up with is a big blob that has your operating system and target program all in one image. And the other way is you have the operating system and a loader, and then the loader can load the target that is to run from network, from a SD card, or even, as we've seen, from a floppy disk. Also, we didn't have time to develop a full automated CGC-like bug finding system, but we really wanted to give the customer some kind of really useful capability quickly. So we went with AFL, which is an industry standard fuzzer. Honestly, since a lot of these things have probably never faced any kind of adversarial input, a whole automated bug finding system is largely unnecessary. A simple fuzzer was going to do the job really, really well. And to make it easy to use, we chose something fairly standardized. The big problem we had is that AFL only works on open source user mode programs generally. And what we had met exactly none of those requirements. And so our next issue is on how do we get AFL to fuzz unmodifiable kernel mode code, which is where our next solution is QEMU. QEMU is a popular open source emulator. It's a whole system emulator that supports a wide variety of CPUs, platforms, and peripherals. Thankfully, it had a whole number of PowerPC reference platforms that it emulated, which turned out to be really handy for us. And because it handles many different processors, QEMU can translate everything to an intermediate language. And in that translation portion, we can leverage it to essentially gain the code coverage we need to use for fuzzing. So during this translation, we can add extra hooks and then have something that can execute and provide coverage for cross-architecture and cross-platform program execution to solve our problem of how do we get kernel code into AFL. There were many previous attempts at combining AFL and QEMU, but neither of them were really adequate for what we were doing. Usually all of them require either source code or to be able to run custom programs in the target. We couldn't do either of those things. Everything had to be done on a completely unmodified target image. And so we ended up being able to combine them together in a single program. And Peter will discuss more details of how we actually did this. And it resulted in several novel solutions for questions like, how do we get a file-based fuzzer to provide input to a whole system that may have many different I/O inputs and outputs? How do we detect a crash? How do we know when a whole system that you're emulating has stopped? Because you have to have a certain pause point when you kind of give up fuzzing and go to the next thing. It's not just going to exit. And what do we do about all of those pesky devices that we can't really emulate? So now that we described the how, Peter's going to take you into a deep dive about the why. And we'll start our incredible journey into the design of PowerFL with a context about why a feature exists and not just how it works. And as we discover a solution to each subproblem, we're going to get a list of whole new problems that come up with that we have to address. And before I hand this off to Peter, I wanted to say that a lot of our requirements were driven by the need to rapidly develop something that works and works well. And so we're definitely open to suggestions and improvements. And with that, give it a go, Peter.
Thank you. Is this, okay, yeah, thank you. So as Artem kindly introduced, our overarching goal was to fuzz PowerPC VxWorks targets. And a kind of funny thing about this whole project was that neither of us had any experience whatsoever with PowerPC or VxWorks. And so it's kind of like going in with two unknowns. But we had a lot of experience with x86, and we wanted to kind of mitigate the risk on this project. And so I'd say we graciously delivered extra capability and said, we're only going to solve one problem at a time. We're going to do VxWorks on x86, and then when that's working, we're going to port that capability over to PowerPC. And that turned out to be a pretty good strategy. It worked for us. There was still a whole host of issues in terms of like booting PowerPC that you don't get with x86 because the support is just so good on QEMU. But so now we only had one problem instead of two, fuzzing VxWorks. And so ideally, we wanted to just run AFL fuzz on a VxWorks target. And Artem has already told you that VxWorks is this supervisor mode program or library. It's like it runs in the kernel, runs in ring 0. And AFL is really just like a user mode file-based fuzzer. And so how do we connect the two? Our approach was really just literally we're going to connect them. We're going to take the source code of AFL. We're going to put it right on into QEMU. It's going to run as a separate thread. And then we have this kind of communication between the two. So QEMU will start up. Our target is about to run. In theory, it gets to the point where it needs input, swap over to AFL. AFL provides some mutated input, signals back. Execution continues, emulated, and then this kind of loop repeats itself. And part of this process that I just described, the whole emulator booting up, getting up to the point of the first input, involves a lot of sort of redundancy and mostly deterministic execution. And by the way, here's kind of like our ideal, what we wanted to see at the end, and we'll have a demo to show you. But what we really wanted was to avoid this redundant execution that happens every time you boot up a VM up to the point where the first input comes in. And the goal is really like, we want to fuzz and we want to perform as many executions as possible. And so any execution that's sort of completely unrelated to user input that happens before the first input comes into the system is irrelevant to us. And it's just wasted time and it's just reducing our throughput. So the first kind of solution that we had was to say, we're going to use QEMU's snapshot and resume capability, and we are going to snapshot the VM just before we get the first user input. And then every time we have a new mutated input, we're going to resume the VM from the snapshotted state. And this sounds great in theory. This is basically how user mode fuzzing works with AFL's fork server. There's a read system call, and it just sort of kind of waits there for new input. And so we wanted to just kind of take that to the VxWorks target. But then we have the question, like where is the first user input? And this is sort of something that I would say everyone kind of takes for granted in user space. It's the read system call. It's reading from standard input, or it's reading from a very specially named file. You pipe the file into the program and things go boom, and it just works. Whereas in VxWorks, we have no kind of concept of where, like what specific function or code is involved in reading the input. And so we needed that same analogous concept of there is this read system call. We needed that kind of semantic visibility to know that a certain event is happening in the guest, in the target, so that we can interpose on this event. And this notion is important for other things. Like if you have in user space, you get a segmentation fault, your program crashes. In a kernel, you get an exception, and it kind of gracefully handles it and keeps going. So we also needed visibility into like exception handlers so that we could catch crash, the equivalent of crashes. We needed visibility into the scheduler to see tasks. And this all kind of boils down at the lowest common denominator to we needed the ability to just hook in at arbitrary points of the execution. And so we implemented a instruction granularity hooking system. On top of that, we did function granularity, where we could hook into kind of semantically at the beginning of functions. We could attach ourselves to the return of functions, inspect arguments according to the ABI. And this ended up being probably the most useful tool in our toolbox to do the next set of problems. But this all assumes something, which is that we can identify the things that we actually want to hook. There's all these functions, and when we started off, we had Tornado, which is a development environment, and we'd compile a test program that would like read some input in some simple way, and it had debug symbols and things were great. And the client provided us these firmware images, and they were stripped. They had no symbols. So we had this fancy hooking system all ready to go, and we didn't know what to hook. And so we had to find a way to figure out, we know we want to hook this, IO get function. We know we want to hook the schedule function. We know we want to hook, the page fault function. How do we find that? And so it's pretty messy, to be honest. I think in retrospect, we should have used maybe something like bindiff, and there's some other, like the Rose compiler has a good function recognition system. So we kind of did an ad hoc solution to kind of symbolize our firmware images based on a baseline VxWorks that we built. We used IDA flirt signatures, which is pretty like rough version of like regular expressions, I would say. And we also did some other things, like we'd say, we've observed that lots of functions in VxWorks have log statements in them, and their logging format strings are uniquely identify the functions that use them. So if we can kind of match cross-references that way, then we can match functions. And this is like an 85% solution. But it gets you sort of far enough, and then the rest, a bit of manual sort of looking at things in your favorite interactive disassembler helps you resolve all the remaining problems. A complementary problem is that we also need to handle the fact that given a new firmware image, not only is it going to have missing symbols for functions we know, it's going to have missing symbols for functions we don't know. Like it's going to call functions that initialize devices that we are not prepared for, that we have no idea how to handle. Like maybe they read things in some really strange way. And we needed to have a way to automatically handle like arbitrary devices. And the solution is almost going to sound naive, but it makes sense at a high level with a bit of perspective. So our solution to handling most unknown devices is that if you can identify the driver initialization of that function, then we are just going to stub it out basically into a no-op. We will say, okay, hook this initialization function and make it immediately return with a status of okay. And this sounds completely broken. Like you're not initializing the driver. How could the remainder of the program ever work? But in context, you have to see that sort of VxWorks is kind of like a big object-oriented system in a lot of ways. Like most drivers, they follow an interface or a specification. They register a certain number of functions, and then at least a nicely coded, well-behaved program running on VxWorks will interact with the driver via a standardized interface. And so it's those standardized interfaces that we try to symbolize, that we try to hook at sort of this higher level and model. And so if we're hooking and modeling at this higher level where the program is actually interacting with, then we're never going to actually execute into this uninitialized driver. Like we are going to say provide, we're going to like just poke bytes into the guest memory address space anytime input needs to be read, and kind of just skip over a lot of these higher level interfaces. And so that turned out to be a really kind of a nice win for us. But yeah, so we needed to, again, identify these functions that are doing this device initialization so that we could stub them out. This was really sort of kind of a bit manual, and it came up a lot when we were doing our initial port from x86 to PowerPC. We said, okay, we got this thing working on x86, and there's a bunch of totally different device initialization that we had manually stubbed out on x86, and it ends up being completely different on PowerPC. And so what we came up with was more of like a interactive and visual approach where we could take a baseline, like let's say you have something working, our baseline x86 thing, or maybe a baseline PowerPC firmware image that we have working. We could take a trace of it. And then you have your unknown one, your new target that you're trying to bring up. We take another trace of that, and we have this ability to basically diff the traces to present a call graph and show, okay, here's where everything, like black is things that are new in our new target, blue is things that are only in our old target, and green is, I guess, things that are common between both targets. And so you can kind of visually see, kernel init is calling this unknown function, and then it eventually calls like another function that's associated with registering a device. So maybe that function that we don't yet know, we can just stub that out. And so that's sort of like a visual but still manual way to kind of look at the state of things and see, this is some driver setup code, this is something I need to stub out. I think longer term, we could also do this just as well with a bit of static analysis. Anyway, so let's just say everything is going well right now. Like we've got everything symbolized. We've got our hooking devices are just muted or modeled. Things are generally going well. Now we've gotten to the point where we actually need to feed input into the target. And Artem already said that this is a kernel, and most, like how do you get input into a kernel? It might accept input in a variety of different ways. It could take it off ROM, it could take it off the network, might need to like mount a FTP file system and then start reading from there. And we certainly don't want to run an FTP server. So we needed a way to kind of get input into the guest. And another thing is that, just to really underscore it, is that VxWorks is not it's not like a monolithic kernel like Linux that you can just dynamically load a new module in. It's not prepared for something like VMware tools. It's not prepared with like a hypervisor support for VirtIO drivers. So like we can't just load a driver in there that's ready to take our inputs. So we needed to kind of make like what's basically a transparent I/O pass-through mechanism. Like we needed to get bytes from the host into the guest, and our approach to this was modeling at the function level. So we would look for all sorts of I/O related functions, and we would kind of come up with our own shadow concept of this is the state of the file system. This is the state of, these are all your open file descriptors. These are sort of the paths that we can associate with them. We can map those into the host file system so that AFL can, write there if it wants to. We can set up configuration files on the host that just transparently get read in the guest because you might be missing those. And so it just ended up being kind of like, imagine, if you will, that you're interposing on like the read system call, but you have to implement it, and you just start like poking bytes into the address space, and you say return from read when you're done, and that's kind of how it works with a bunch of extra scaffolding. Well, I just explained all that actually, and yeah. Anyway, so now we've got input into the program. AFL is a coverage-guided mutational fuzzer. Like its metric for progress, is did this input cause new code to execute? And if new code executed, then we should prioritize the input for future mutation over other inputs because maybe they're not as interesting. And QEMU is basically like a big JIT. And so we just use the same kind of thing, the same instruction granularity instrumentation that sort of was the backbone of our function hooking. We use that to implement basic block granularity coverage metrics that could then kind of work into AFL, so you get like edge coverage, approximately the same way AFL does it. Honestly, I think we did it better. Come ask me about it if you want details. One interesting thing that we added support for was we made it sensitive to self-modifying code. And this will sound maybe unusual to you, like why would you expect there to be self-modifying code? And it's actually not unusual because a lot of VxWorks things come with this ability to load a shared library or load a shared object, unload it, and then load a new one. And so it's sort of like, that's kind of like self-modifying code. You end up with code overlapping in time at least. And so we support that. And we had this one problem though, where we'd kind of see spurious code coverage reports saying like, we'd run the same input and it'd say new coverage every time. And we're like, what's going on? And it was interrupts. It was annoying. It's like signals in user space, but like a timer interrupt coming in and just interrupting your thing and adding these false edges into your coverage bitmap. We handle that just by checking, are we in an interrupt context? If so, ignore. I think there's other approaches. Come up and talk with me later if you want to talk about those. Anyway, so we're finally wrapping down our journey, and we're at the point where we can provide inputs. We got our first input into the program. We've ignored all sorts of devices, everything. It's all going great. It's running. It's running. It's running. It's running, and it just never stops running because it's a kernel. Kernels, they just kind of run forever. They go into maybe an idle loop, and if you're on x86 VxWorks, there's a nicely named function called idle, which you would be able to use to detect this. But in PowerPC VxWorks, there is no such function. So how do we detect when the program is done? Or more specifically, how do we detect when the program is done being influenced by user input? And so here we just sort of built on top of our way of tracking code coverage. So instead of tracking edge coverage or code coverage, we took it more as let's track path coverage. And let's just say that we are going to see, does the program execute the same path of code between two calls to the schedule, the task scheduler? And if we see the same path get executed multiple times in a row, then we'll just assume it has gone idle. And worst case, if we don't see this, we'll have like a pretty conservative timeout. And the way we implement this is with a pretty much a summary counter or summary number. And so when implementing code coverage with like AFL style code coverage, you kind of do like a bit of like you have a random number that you kind of hash and flip a bit. And we could take the same random number or pseudo-random number and kind of mix it in continually every time a block executes. We can mix this value, this random number into our summary value, and it ends up being a kind of a summary coverage. And save it off every time we get to the schedule function, reset it, and then keep going. And if we observe the same values over and over again, the same path has been executed. I think that was kind of particularly clever, and it worked really well. Anyway, so Artem can give a quick demo.
I'm going to make this super, super quick because we're running low on time. So this is the simple test program we're going to be going after. I don't think we'll have enough time to wait for it to actually find this, but eventually it will trigger a vulnerable function. Essentially, this is just going to be effectively the AFL prompt. This is technically the QEMU display in the back. You actually can't see what's going on because it's fairly quickly loading and saving snapshots, but it is doing its thing. You might notice it will pause occasionally. On macOS, there's a slight bug where it freezes. It only happens in Mac QEMU. Normally we run this on Linux, so we didn't really care to debug it much. But yeah, it's doing its thing. I can terminate it. And yeah, this is the thing. It's going after this PowerPC built VxWorks image. All right, let's get back to talking to not take up too much time.
All right, so Artem introduced at the beginning that this is a prototype. And so I think the path from prototype to production is really a few steps. One is speeding things up. I said earlier that QEMU is basically a big JIT compiler, translates machine code into its TCG representation, and it does this every time. And I think we could do this ahead of time, and that would shave off a bit. There's a bunch of other things related to ahead of time translation that we could definitely do. Emulation support for new devices. I think really we just need a lot more tooling to support a person bringing up a new system. Modeling is a big issue, and I think there's some room for exploring S2E to help support these unknown devices. Like if we can just say, oh, this is symbolic, see what it does, and use that as a way of helping the user get up and running. And this one is really a tricky thing, handling new and unique input sources. Like if we had scatter gather, memory mapped I/O, that would be kind of tricky to handle. We didn't encounter that with our customer, but I'm sure it's a real thing in the real world. And interrupt timing as a source of inputs would also be an interesting source. Where where you're fuzzing a schedule, basically, of interrupts. That's another thing to bring, to make things work more in a production quality system that we didn't have to address in our prototype. And finally, this is probably the easiest one, is actually keeping everything up to date. We depend on 2 open source projects, AFL and QEMU. At the time, we took the master branch of QEMU and we took the latest AFL. We ripped a whole bunch of stuff out of AFL to make it fit into our thread-like model. And with QEMU, we actually tried to keep our changes few and far between when it came to actually modifying the source code proper, and we kind of isolated all our code. So I think upgrading to newer versions would be very straightforward. Fun fact is actually we found bugs in both systems when trying to do this. For example, AFL would ignore crashes when it would try to minimize a mutated input. And that was a pretty serious mistake. And there were some TLB issues on PowerPC support in QEMU, I think. Anyway, so finally at the end, we made this big fuzzing system. We did it pretty quickly, but I'm pretty proud with what we came up with. We solved a number of really unique challenges, I think. I think our approach, I think the approach we've taken is actually broadly applicable. I've heard anecdotally from a colleague that has done similar things that, in fact, you can sort of handle new devices by modeling them one at a time. It doesn't sound scalable. Like it sounds like, oh, geez, it's going to be a lot of effort. But there's sort of a critical point where after which, like once you've handled a certain number of them, the rest are kind of pretty easy to handle. And really the next steps for our system is to just sort of evolve it into beyond our prototype status, really. Just make it easier to bring up a new target, make it easier to run the new targets, to hook into things, and speed it up. So yeah, I'm Peter Goodman, that was Artem Dinaburg, and you can always reach out to our R&D director, Trent Brunson, and Twitter, blog.